Right. In Chapter 6, we're going to talk about linear functions. And I just want to show you this excerpt from page 18 that we've seen linear functions before. A linear function satisfies additivity and homogeneity. The linear function applied to the sum of two vectors is the sum of the linear function applied to each vector. The linear function applied to a scalar multiple times a vector is the scalar multiple times the linear function applied to a vector. Now in Chapter 6 we see these two properties combined. Here we have a linear function from two vector spaces. Now we're specifying that in fact we're looking at vector spaces. And the linear function of a linear combination is the linear combination of the functions of the individual vectors. So this combines additivity and homogeneity together. If you let s equal 0, you get homogeneity. If you let r and s be 1, you get additivity. And from additivity and homogeneity you can derive this formula. So those two properties are equivalent to this linearity property on linear combinations. And here we make a point that was made back, I think, in Chapter 1, that linear map, linear operator, linear transformation are basically the same thing, that people tend to use different names in different contexts. And sometimes they may also use homomorphism. Typically we'll represent a linear function by capital L, but sometimes just by F also, depending on the context. So let's look at some consequences. Linearity is a very powerful property of a function because, for example, if I know what a linear function does to one vector, I know what it does to an infinite number of vectors. Right? If I have L of 1, 0, then L of 2, 0 is what? Well, look down here. For example, L of 5, 0 is L of 5 times 1, 0, which by the linearity property is 5 times L of 1, 0. But L of 1, 0 was 5, 3 up here. Right? So L of 5 times L of 1, 0 is 5 times 5, 3 is 25, 15. Right, so we get an infinite number of outputs just from one. Also, if we know the linear function applied to two different vectors, we can get the linear function applied to any linear combination of these two vectors. For example, we know 1, 0 and 0 plus 0, 1 is 1, 1. So I know what L of 1, 1 is. How do you find L of 1, 1? Well, I'm going to use the additivity property. L of 1, 1, I just express 1, 1 as the sum of 1, 0 plus 0, 1. Those are the two individual vectors here. And then by the additivity property, I can basically distribute this L over those two vectors. And I get 5, 3 from the first, 2, 2 from the second. And I add these with ordinary vector addition and get my result. Now here we take that even farther. For example, any vector in R2 can be expressed as a linear combination of 1, 0 and 0, 1. Right? X, Y, any vector in R2 is x times 1, 0 plus y times 0, 1. Just add them together and see. But if I know what L does to 1, 0 and what L does to 0, 1, I know what L does to any vector in R2. Right? So that's just two functional values tells me what L does on every vector in the space. So I can write L of xy. I just replace xy with this expression in terms of 1, 0 and 0, 1. Then I use the linear combination property to re-express that as a linear combination of L10 and L01. But I know L10, I know L01. L10 was 5, 3, L01 was 2, 2. I just use the linear combination property to get my result here. And in fact, you can see that L acts just like the matrix 5, 2, 3, 2. If you multiply 5, 2, 3, 2 times xy, then you will get this result. So what we're coming down to is that basically a linear function is another way of saying a matrix. A matrix is another way of expressing a linear function. Okay. Right. So just the same way that a linear function on two vectors in R2 specify the linear function completely, so the linear function acting on three vectors in R3 will determine the action of the linear function completely. So you need two vectors in R2, three vectors in R3. Can you guess the general rule? Well, that's what it says down here. If you have domain Rn, you can choose n different vectors And the value of the linear function on those n vectors will give you the linear function everywhere. Now, you can see the nice form of these vectors. In fact, these vectors are the columns of the identity matrix. And in Rn, it's the same thing. If you take this particular nice form of vectors and use that as your vectors, you will, well, it's just basically a nice choice. It will be easy to specify the linear function on all vectors if you know the linear function acting on each one of these vectors.